In our last several videos, we've looked at finding a polynomial, finding the zeros of a polynomial given a higher order polynomial. And we remember that a zero is the value of x that if I plug it into the function will make the entire function equal 0. And we saw that if those were real numbers, that number was also the x-coordinate of an x-intercept. What we're going to look at in this video is going the other way. What if I'm given some zeros, and I need to find a polynomial that would have a polynomial that would have those numbers as zeros. So let's say that I know that 3 and -2 and 1 are zeros of a polynomial. And we know that if a is a zero of f of x, we know that by definition that means f of a equals 0. And we know that x minus a is a factor, one of the things that I could multiply together to get that function f of x. And we also know that if a is a real number, it shows up on the real number line. It would show up on a graph as an x-intercept. So if we know one of those things, we know all of those things. So how can we use that to find our polynomial, f of x? Well, if I list my zeros, 3, -2, and 1, then I can find my factors by taking each one of those zeros and subtracting it from x. So I'm going to have an x in each of these factors, and then I use my zeros to figure out what the rest of the factor is. You see if you can fill the rest of those in. And so I have x minus 3, x minus -2, which is x plus 2, and x minus 1. So if I just want to leave my polynomial as a factored polynomial, then I'm done. I'm finished. I have found the polynomial. But if I need to know what the polynomial is as x cubed and x squared and so on, I can actually multiply. That's what these pairs of parentheses mean. They mean multiply. So I can choose any two factors. And I'm going to go ahead and choose the first two and FOIL that out. The x minus 1 just drops down. Then I can combine like terms. And then I can distribute every term here times every term here. X squared times x is x cubed. X squared times -1, and so on. And then combine like terms. And that is a polynomial that has 3, -2, and 1 as zeros. Let's try another one. Let's say that we want to find a polynomial
rational coefficients. We don't want to have any imaginary numbers or square root of 3 or irrational numbers as coefficients in our polynomial. So we want to have rational coefficients with zeros, 4 and 2i. Now, if I try to just make my two factors, if I try to just say, all right, I'm going to write out the two factors that would go with this. You go ahead and do that. Remember, we have x minus whatever the 0 is. So you go ahead and write the two factors we have so far. And we have x minus 4 and x minus 2i. If I FOILed that out, I'm going to end up with positive 8i, negative 2ix. I'm going to have i's as coefficients. And we're asking for rational coefficients only. So I have to think about this 0 right here. This is an imaginary 0 because of the I. Remember, whenever we tried to solve a quadratic equation, and we isolated our x squared and took this positive or negative square root, that we always ended up with the positive or the negative value. And when we use the quadratic formula, if this whole part is not a real number where we can just get a rational number where we can get two rational fractions, we still have this plus or minus part. So what we're seeing is that every time we have an imaginary with an I in it or an irrational 0 with a square root of 5 or square root of 11 or something that doesn't simplify, we always have the positive and the negative version. Those are what are called conjugate pairs. So looking back up here at my list of my list of zeros, if I have 2i as a 0, I must also have its conjugate, minus 2i, as a 0. So that gives me a third factor, x minus negative 2i, which is x plus 2i. So if I were just listing the factors, I would be done. I would be finished here. That's my polynomial. But if I need to multiply it out, find the polynomial that has those three zeros, I'm going to just multiply. So I'm going to multiply the conjugate pairs first. And if I do that, I want to multiply the conjugate pairs first because it's going to cancel out those imaginary numbers. So I have x times x is x squared plus 2i minus 2i minus 2i times 2i is 4i squared. So I'm still just dropping down the x minus 4. And then 2i minus 2i is 0. So I have x squared minus 4i squared. Remember that I squared is the square root of negative 1. So I squared is negative 1. So this whole thing, minus 4i squared, becomes plus 4. And notice, Down here, when I solved this quadratic equation, x squared plus 4, I got plus or minus 2i. So it makes perfect sense that if I FOIL it back, I'm going to get x squared plus 4. And then now I can use the distributive property and multiply x times each term, negative 4 times each term. And get back in standard form. And I have my polynomial. Let's look at one more example. Let's say that we have a polynomial f of x and on this one we have a graph. And we know that this graph crosses the x-axis at negative 5, at 1, and at 3. And we further know that it crosses the y-axis at 30. And it looks like this. And we want to find the polynomial, f of x. In our previous couple of examples, we were given the zeros. We were given a list of zeros. We created our factors and we multiplied to get our polynomial. On this one, we're not given a list of numbers, but we know that if a is a 0 and a is a real number, a comma 0 is an x-intercept. And it goes the other way too. If we know this, we know this. So I'd like you to look at the picture and list the zeros. And we see that our zeros are negative 5, 1, and 3. So if I want to write my polynomial, f of x, I may have some constant multiplied through, a, times each of my factors. You go ahead and write your factors. X plus 5, x minus 1, x minus 3. So my polynomial, if I were to list this out, would be a times each of those numbers. And I'm going to just leave this in factored form. Rather than multiplying the whole thing out, I'm just going to leave it in factored form. Let's talk about a here. That's where the y-intercept comes into play here. We know that f of 0 is equal to 30. We have the point 0, 30. That is our y-intercept. So if I were to plug a 0 in for x here, here, and here, I would have 5 times negative 1 times negative 3 is 15 times a. But we know that f of 0 is 30. So if we solve for a by dividing by 15 on both sides, we get that a is equal to 2. So that tells me that my polynomial is 2 times x plus 5 times x minus 1 times x minus 3. And then I can FOIL this all out. I'm just going to choose the first two to multiply and get a quadratic. X squared plus 5x minus x is plus 4x minus 5, still times x minus 3. And then distribute here. Let's see, minus 12x minus 5x plus 15. Combining like terms. And then finally distributing the 2. And this is my polynomial that would have that given graph. And notice that my y-intercept